Okay, let's have the solution to example 59 about counter diagonals. For the indeterminate plane truss shown in the figure, SAT-002, all cross diagonals in panels E, G, and GI are made of ropes. Determine the stress in the active tension diagonal in the third panel from the left. Determine the stress of member DF in kilonewtons, and determine the stress in member EG. So since the load is at the center, the vertical reaction at A and at L will be equal to 24 kilonewtons as shown. Therefore, the panel shear in the third panel from the left is 24 kilonewtons downward. So this is a unique problem because in our experience, the bottom and top chords are horizontal and the counter diagonals are symmetric. So in this case, what is important is the panel shear is downward. Therefore, DG, the vertical component of DG should be downward. So DG is tension and EF, the vertical component of EF is also downward. So EF is in compression. Therefore, because the diagonals are made of ropes, EF will be automatic zero and DG will be the active tension diagonal. So this is the active tension diagonal. FEF is zero, but in this panel, take note that DF has vertical component, so we should consider that, and vertical and horizontal component, so therefore EG must also be involved. So the free body diagram would be this, the complete free body diagram. So let's compute for the angle that DG makes with horizontal as well as DF makes with horizontal instead of determining the slope. So theta DG is arctan of 7.5 over 6. Theta DG is equal to 51.34 degrees, while theta DF is arctan of 8 minus 7.5 over 6. So theta DF is arctan of 0.5 over 6. So theta DG is equal to 4.764 degrees. We cannot determine right away the magnitude of the active tension diagonal FDG because of the other unknowns. But if we sum up moments about D, we answer letter C first, we can solve FEG. Considering imagine that it is cut in this panel, so FEG times 7.5 equals 24 times 12. That would be the equation. So the first equation is FDG sine of 54.34 degrees minus FDF sine of 4.764 degrees equals 24. That is the vertical component of FDG, which is going down because is supposedly equated to 24 when DF is horizontal, but because DF has also vertical component and we assume it is upward, so we have to subtract because the vertical component of FDG, which is downward, must be equated to 24. Then because FDF is also considered, so we have to subtract the vertical component of FDF, which is FDF sine 4.764, and the net result should be equated to 24. Then summation of moment about D equals 0 counterclockwise positive to solve for FEG. So FEG times 7.5 equals 24 times 12. Counterclockwise equals clockwise. So we can now compute FEG, which is in tension, 38.40 kilonewtons tension. Now that we have found FEG, we can find FDG actually if we extend DF and find the point of intersection between the extension of DF and EG. Then we sum up moments about that point, but because it is a tedious job to do, we first solve for FDF by summing up moment about G because DG and EG meet at G. So considering the section in this panel and we sum up moment about G. FDF is inclined but by principle of transmissibility, let's move it at F. There are two components, horizontal and vertical. The vertical component passes through G, so don't mind only the horizontal component. So summation of moment about G equals 0, clockwise positive. Remember that dF is moved to F, and the horizontal component produces clockwise moment, FDF, cosine of 4.764 times 8, then plus 24 times 18, and equals 0. So solving for FDF is equal to negative 54.19 kilonewtons, or FDF is 54.19 kilonewtons compression. Then, knowing the magnitude of FDF, we substitute it into equation 1. FDG sine 51.34 degrees and minus negative 54.19 sine of 4.764 degrees equals 24. Then we can now compute FDG. FDG is 24.97 kilonewtons, or FDG, the active tension diagonal with a magnitude of 24.97 kilonewtons. So this is counter diagonals, and I hope that you already encountered this type of problem. It's a matter of statics. So the principle is same, that the vertical component of tension should be vertical component of the active tension diagonal should be equated to 24, but because the member DF is not horizontal, it has vertical component, so using statics, we have to subtract the vertical component of FDF from the vertical component of FDG before equating it to the panel shear at this third panel from the left. Then the rest will be statics. That's it.